Have you ever wondered how those cranes that lift so many tons of weight are so tall? How can they be assembled? What's the science behind it? How do they work? And more, get ready to learn the answers to all those questions you're asking yourself. To build a tower that touches the clouds, you need a steel arm capable of hoisting tons to its summit. But to raise that arm, you would need another arm, even more powerful and taller. That doesn't exist. A chicken and egg problem, forged in steel and planted at the feet of gravity. This paradox for centuries limited humanity's dream of ascending, until engineering came up with the boldest answer, a machine that didn't need to be lifted because it would learn to climb using its own body, an iron creature that grows by feeding off the building it helps to construct. Today, we'll show you more than just screws and hydraulic jacks. We'll take you to the heart of this act of controlled levitation, hundreds of meters above the ground, where a mistake of millimeters can lead to tragedy, and where a handful of men and women guide a self-building giant. This is the true story of how a tower crane conquers the sky. The ascent begins now. The giant's foundations, the paradox and the route, from the window of a neighboring skyscraper, in the metallic silence of an urban dawn. The image is almost an optical illusion. A skeletal structure, a rusty red or a warning yellow, rises from a sea of scaffolding and fresh concrete slabs. It isn't planted in the ground, but seems to sprout from the very heart of the building under construction, several hundred meters above, where the air is already thinner and the wind sings with a different whistle. Its horizontal arm, the boom, extends like an immense finger sweeping the sky, defying the curvature of the earth. It is a tower crane, and its mere presence in that place, at that height, is a challenge to the most basic logic. Any child playing with blocks would understand. To place the last block on top of your tower, you need to already be up there, or have a long enough arm. But what if that arm weighs more than 200 tons? What if there is nothing higher that can lift it? Observing that solitary silhouette against the city's sunset raises the question that has obsessed builders since the first man stacked one stone upon another. How on earth did it get there? The answer lies not in a single trick, but in an engineering revolution that began, like all great journeys, with a seemingly unsolvable problem and a first step literally buried in the darkness of the earth. The builder's paradox. Who lifts the lifter? For millennia, height was a battle against gravity and matter itself. The Egyptians with their earthen ramps and stone sleds, the Romans with their pulleys and wooden scaffolding, the Gothic master builders with their ingenious squirrel cage cranes, all faced the same fundamental limitation. Your lifting tool could not be taller than the structure you were building, and raising it beyond certain limits was a titanic, if not impossible, featuring the crane was an earthly servant. With the Industrial Revolution and the arrival of steel and reinforced concrete, the horizon dreamed of by architects and urban planners shot skyward. But the paradox was reborn, sharper than ever. To build a 50-story skyscraper, you need a crane on the 50th floor to hoist the beams to the 51st floor. But to put that crane on the 50th floor, you would need another crane on the 51st floor. An infinite loop, a logical dead end. The most powerful mobile land cranes, those 100-meter-long behemoths, have an insurmountable physical limit. Beyond that point, their sheer size and inherent instability doomed them. It seemed that humanity's ambition to reach for the sky would find its ceiling not in the strength of materials, but in this simple matter of logistics. The dream of ever taller skyscrapers crashed against an invisible wall, the impossibility of positioning the celestial worker at its work site. A machine was needed that not only worked at great heights, but could reach them under its own power, or rather, by constructing its own means as it ascended. Birth of a crane climber. The concept that broke the limit. The solution, as so often happens in engineering, came not from a single stroke of genius, but from the slow and persistent evolution of a simple idea. If you can't lift the entire crane, what if you only lift its operational section? Imagine a caterpillar track. Its body is long, but it moves by anchoring one part of itself to the ground and extending the other forward. Now apply that image to steel and the sky. The germinal idea was this: A crane with a fixed mast and cab, a boom, and counterweights that together could detach from the mast and ascend it, like a ring climbing a pole. In the space left by the detachment, a new mast section would be inserted. Then the upper assembly would rest on that new section, and the cycle could be repeated. The crane wouldn't be hoisted, it would be a climber. It would self-assemble. This concept, which seems obvious to us today, required decades of refinement in mechanics, metallurgy, and hydraulics. The first prototypes in the mid-20th century were crude and risky, but they demonstrated that the paradox had a solution. It wasn't about brute force, but about mechanical intelligence and a choreography of absolute precision. The tower-climbing crane ceased to be a static tool and became a growing organism, a symbiotic parasite that fed on the building's very structure to rise and, in turn, shaped it. The architect of the sky was born. But every organism, however revolutionary, needs a solid, immutable starting point from which to begin its journey into the unknown. Where it all begins, excavating immobility. Before the first glint of steel flashes in the sun, before the first truck unloads its cargo of modules, the crane's fate is written underground. This isn't just a hole for pouring concrete. It's the creation of an artificial mountain of stability, the anchor that will defy all the forces heaven and earth can conjure for years to come. The location is chosen with surgical precision, marked with lasers on the foundation slab of the future skyscraper. The excavators arrive and begin to bite into the earth, but they soon give way to deeper, more forceful methods. A rectangular pit several meters on each side may be dug, but its depth is what's astonishing. 15, 20, sometimes 25 meters into the subsoil. It's like digging the foundation for an 8-story building, but only to support a single leg. In the most demanding projects, deep piles are driven around the site, ensuring the foundation rests on bedrock, not shifting earth. Then, within that shadowy pit, engineers weave the skeleton of stability. They lower, section by section, a steel cage of reinforcement so complex and massive it resembles the root of a giant metallic tree. Large diameter corrugated steel bars are interwoven and welded together, forming a dense tangle that can weigh more than 50 tons on its own. This cage is not just reinforcement, it is the nervous system of the future force transmission, designed to distribute the incredible torsional, bending, and shear loads the foundation will endure. Pouring day is an industrial ceremony of relentless rhythm. Concrete mixer trucks follow one another in a continuous procession, their rotating nozzles unloading a grey river of ultra-high-strength concrete, often reinforced with fibers or special additives. The pour cannot be stopped. It must be a monolithic block, without cold joints, without weak points. For hours, the concrete flows, filling every nook and cranny of the steel cage, until the shaft becomes a buried colossus. The final mass can exceed 400 tons, a weight comparable to that of an adult blue whale or the Statue of Liberty without its pedestal. Its cost, in materials and labor alone, can reach €300,000, the price of several single-family homes. But this cost is the first and non-negotiable installment of the crane's life insurance. Upon this block of absolute stillness, upon this root of stone and steel driven into the city's heart, everything that follows will rise. It is the promise of immobility in a world of conflicting forces. The first heartbeat, assembling the heart on solid ground. With the foundation cured and hardened, the structure welcomes its first special guests, the crane modules. They arrive in convoys of low-bed trucks, escorted by warning vehicles. Each mast module is a hollow steel piece, square or triangular in cross-section, measuring between 3 and 6 meters long and weighing up to 10 tons. They resemble giant construction pieces, with perfectly machined edges and bolt holes drilled with clockwork precision. Protruding from the center of the concrete base are steel anchors, the shoes, where the first module will rest. This is where the tower crane receives its first upward push, aided by a conventional crane, a high-capacity mobile crane that will be its mother during this earthly infancy. With slow, deliberate movements, the mobile crane lifts the first module and places it onto the anchors. It is a moment of absolute precision. The holes must align perfectly. Once in place, teams of erectors approach with their hydraulic torque wrenches. These aren't ordinary bolts. They're high-strength bolts, as thick as a man's fist, tightened with precise force, measured in Newton meters. Under-tightening and the joint will give way under load. Over-tightening and you can damage the threads or the steel itself, creating an invisible point of fatigue. The sound of the hydraulic torque wrench is a dry, metallic click, the sound of safety being assured. Module by module, the tower grows skyward. At 10, 15, 20 meters, the most critical component is installed, the turntable. This is the mechanical heart of the beast. A massive roller bearing, a forged steel disc that will allow everything mounted on it, the cabin, the boom, to rotate 360 degrees smoothly and with control, supporting unbalanced loads and the force of the wind. Mounting it requires perfect alignment with the mast shaft. Any deviation, however slight, will be amplified with height, turning the rotation into a potentially catastrophic wobble. Installing the turntable is a ritual of laser leveling, millimeter-precise shims, and infinitely patient adjustments. It's the moment the tower ceases to be a pile of steel and becomes a machine with a purpose. The birth of the boom and counterweight. Now comes the moment to give the beast an arm. The boom, that iconic horizontal arm, arrives in sections. Each one is a steel lattice girder, a framework of triangles that maximizes strength while minimizing weight. It can measure up to 80 meters in total when complete. Assembling it on the ground would be impossible due to its length, so it's done in the air. The mobile crane lifts the first section of the boom, the one closest to the tower, and attaches it to the turntable. It's a delicate operation because this piece, which can weigh 20 tons, must be perfectly horizontal and aligned. Then, using the first section as a fulcrum, the subsequent sections are hoisted and connected, extending the arm toward the horizon like a metallic tentacle taking shape. While this is happening, at the opposite end of the turntable, the counterboom, the counterweight is being prepared. Without it, the crane would tip forward the instant it tried to lift any load. The counterweights are massive blocks of pre-stressed concrete or steel, resembling the bricks of a giant. They are carefully stacked, calculating precisely how much weight is needed to balance the empty boom, and later, the maximum load it can carry at its far end. This balance is not static, it is dynamic. The trolley, the mechanism that slides along the boom carrying the hook, constantly changes the point of application of the load. This is why the control systems are so complex. They must know at all times where the trolley is and what weight is hanging from it to ensure that the overturning moment never exceeds the stabilizing moment provided by the counterweight. When the last section of the boom is secured and the last counterweight block is in place, the iconic silhouette of the tower crane is complete. It stands tall, perhaps 40 meters high, imposing yet still vulnerable, like a teenager standing on its feet for the first time. It has form, it has muscle, it has a beating heart. But it doesn't yet know if it is strong. The wind test. When the giant stands up for the first time, before a single steel beam is delivered to it, before the future of the skyscraper is entrusted to it, the crane must undergo its baptism of fire, or rather, of wind and strength. The engineers take control. The process begins with a meticulous visual inspection of every weld, every bolt, every cable. Then come the static tests. Deformation sensors are placed at key points on the mast and jib. With the crane in its most unfavorable position, jib perpendicular to the prevailing wind and trolley at its most extreme position, it is subjected to progressively increasing loads. No construction materials are used, but rather calibrated test weights, concrete blocks, or steel of known mass. These are raised slowly, and the sensors measure the deflection, the bending of the tower and jib. Every millimeter of displacement is compared to theoretical calculations. A discrepancy greater than a few millimeters may indicate an assembly error, a loose bolt, or a material defect. Then come the dynamic tests. The trolley is moved along the boom under load, the crane is rotated with varying weights, and the brakes are tested abruptly. The safety systems, the load limiter, the overturning moment limiter, the trolley limit switches, are deliberately activated to ensure they function correctly and stop the machine before a dangerous threshold is reached. And of course, there's the wind test. Wind speed is constantly monitored with anemometers installed in the cab and at the top of the mast. The crane is designed to operate up to a certain wind speed, say 50 or 60 kilometers per hour. Above that limit, the operator must allow the crane to swivel freely, disengaging the slewing brake so the structure can orient itself like a weather vane, offering minimal wind resistance and preventing dangerous lateral stress. On its first day, the engineers observe how it behaves in moderate gusts. The mast sways slightly, like a steel reed. This is normal, it's expected. The crucial thing is that this swaying is harmonious, that there are no strange vibrations, creaks, or groans that betray any weakness. When all the readings match the models, when the brakes grip firmly and the safety systems respond reflexively, the crane receives its certificate of life. It has proven that it can support, rotate, lift, and above all, withstand. It is ready to work. But its most important task will not be hoisting steel beams or glass panels. It will be something much deeper and more personal, to begin to grow. But this crane, now firmly planted on its base, has only completed the prologue to its own epic. It has demonstrated that it can support weight, rotate, and operate. However, the building it is meant to help create is barely a sketch on the blueprints. To fulfill its destiny, it must do something no ordinary machine can do. Leave behind the safety of the earth and begin to climb, meter by meter, toward a realm where the rules are written by the wind and vertigo. And for that, he will need a special suit, a hydraulic exoskeleton that will be his ladder to the clouds. The rise of the Colossus. The choreography in the void. The crane is no longer the solitary queen of the empty lot. Around it, like steel chutes reaching for the sun, the first columns and slabs of the skyscraper have emerged. Its first 10, 15 stories rise, forming a well of shadow and echoes where the sound of hammering and welding bounces back. The crane, anchored to its concrete base, operates with clockwork efficiency. Hoisting beams, column after column, pouring concrete into formwork that is like gigantic trays in the sky. But with each new floor completed, a problem looms. The top of the building under construction moves further from the tip of the boom. The angles become steeper. The loads must travel farther horizontally. And a point is reached where it simply cannot reach the farthest points of the new floor without risking stability. The crane, which gave life to these floors, has fallen short. It is being overtaken by the creature it helps to create. If it were a conventional fixed crane, this would be the end of its usefulness. But this machine has a pact with height. It's not meant to be left behind. It's designed to keep pace, to chase the summit. And to do that, it must do the impossible, grow itself in mid-air without external assistance. The moment of the first climb is approaching. It's the moment when the machine proves it's not a tool, but a mountaineer of steel. The climber's suit, the hydraulic frame, and its titanic jacks. The secret to this aerial metamorphosis lies in a device that looks like it came from a suit of medieval knight's armor, but scaled up for a titan. It's the climber frame, or hydraulic cage. Installed directly beneath the turntable, it's an exoskeleton of steel beams that tightly hugs the existing mast. It's not merely supported, it's secured with large diameter pins that clamp it to the mast like a colossal brace. Inside this frame, hidden from view but palpable in their power, are the system's muscles, the hydraulic jacks. These aren't the small cylinders on a garbage truck. They are forged steel columns, with pistons the diameter of which could rival the trunk of a sturdy tree. They operate with oil at pressures so high they could cut through metal if a hose were to burst. Their function is sublime in its simplicity, to act like the elevators of a skyscraper, but for the skyscraper itself. They are connected to a yoke or upper platform, which in turn is rigidly attached to the live part of the crane, everything above the climbing frame. That is, the rotating platform, the operator's cab, the entire 80-meter boom, and the tens of tons of counterweight. In total, an assembly that can easily weigh between 150 and 200 tons. The climbing frame is the fixed fulcrum, the hydraulic jacks are the levers, and the entire crane is the load to be moved. Archimedes dreamed of moving the world with a sufficiently long lever and a fulcrum. Modern engineers gave the world steel, pressurized oil, and a rendezvous point 300 meters high. The moment of truth, the ritual of the vertical leap. On a designated day, when the wind is still and the sky is a clear blue, the time for the ascent is decreed. All critical activities near the crane fall silent. It is a sacred day for the erectors. The ritual begins with the crane using its own hook to hoist a new mast section from the ground, identical to those that form its backbone. This 6-meter, 10-ton piece is delicately balanced and left suspended near the tower, secured with slings to the building's structure, awaiting its moment. It is the egg that will be inserted into the nest. Then, inside the cab, the operator activates a special sequence on the controls. A new sound joins the usual symphony, the deep, powerful hum of the hydraulic pumps of the climbing system coming into action. It is not a roar, but the sound of concentrated, contained force. The technicians on the structure, connected by radio, give the signal. The operator presses a button or moves a lever, and then it happens. The enormous pistons of the hydraulic jacks begin to extend, millimeter by millimeter. There's no sudden movement. It's a slow, majestic liftoff, almost imperceptible to the eye from afar. But from within, it's a controlled earthquake. The cab, the boom, everything you know as the crane, rises. It separates from the mast on which it has rested for weeks. The ground seems to sink a little more. The main physical connection to the earth, that mast anchored to the 400-ton base, is, for a moment, severed. The crane flies, held only by the steel embrace of the climbing frame and the hydraulic force of its cylinders. It's an act of faith in physics and engineering. The moment of maximum vulnerability. This is the moment that takes the breath away from even the most seasoned veterans. For several minutes, the entire working mass of the crane, a weight equivalent to 2 complete diesel locomotives, hangs in the air, separated from the main mast by a gap that grows to 3 meters in height. Stability no longer depends on the solidity of a tower anchored to the ground, but on the integrity of a few frame beams, the strength of the pins that hold it together, and the reliability of a hydraulic system under monstrous pressure. A failure here is irreversible. A failing cylinder, a catastrophic oil leak, a snapped pin would turn that slow lift into a free fall of 200 tons. The crane would plummet onto the building under construction, a cascading collapse of steel that would sweep away floors as if they were made of cardboard, and sow unimaginable devastation. That is why, at this moment, radio communications are reduced to the bare minimum. All eyes are on the pressure gauges, the joints, the opening. Engineers monitor real-time data from the ground. The wind is the ever-present enemy. An unexpected gust striking the boom while the system is suspended could generate a lateral moment for which the climbing frame isn't designed, potentially twisting or even dislodging the entire structure. It's a choreographed dance where a single misstep means utter disaster. The tension is palpable, a steel thread vibrating in the silence thick with anticipation. A dance of millimeters, inserting the piece into the sky. When the hydraulic jacks have extended their full stroke and the space beneath the raised portion of the crane is exactly the height of the new mast section plus a small margin, everything stops. The hydraulic whir ceases. A tense silence reigns. Now begins the most delicate part, the true test of human skill. The installers, equipped with safety harnesses anchored to the structure, move with the caution of felines along the walkways. Their objective, to guide the new mast section, still hanging from the crane's hook, into the opening that has been created. It's not a simple insert. It's a dance of millimeters. The section weighs 10 tons and is a rigid prism. It must be perfectly aligned with the steel wings of the existing mast so that the bolt holes on all 4 sides align simultaneously. To do this, they use guide rods, long steel levers, and their own gloved hands to give small taps, to feel the resistance. The operator in the cab, blindfolded for this task, receives instructions by radio. 1 centimeter to starboard, stop. Now lower, slowly, slowly, stop. The hook descends imperceptibly. The men on the structure watch the fit, squinting, judging alignments more by feeling than sight. When the section is almost in place, they use temporary tapered dowels to align the holes. It's a satisfying metallic sound, a click that signifies precision has been achieved. Only then is the section lowered into its final position. Immediately, the fitters pounce with their hydraulic torque wrenches. They don't tighten one bolt and then another. They follow a specific crisscrossing sequence, like the wheels of a car, to ensure even pressure. Each bolt receives its precise click of torque. It's a sound repeated dozens of times, a mechanical mantra stitching the new piece to the body of the beast. Once all the bolts are tightened and checked, they can breathe a sigh of relief. The crane is no longer suspended by the climbing frame. It now rests on a tower that is a taller module. The cycle is almost complete. The invisible enemy, battling the wind at 300 meters. But at this height, there is an omnipresent actor that never sleeps and shows no mercy: the wind. At ground level, a breeze of 20 kilometers per hour is a pleasure. At 200 meters high, that same breeze has accelerated and become a constant gale due to the lack of obstacles. And a gust of 60 kilometers per hour, common at heights, is no longer an inconvenience. It is a design force. The wind pressure on the immense surface of the boom and tower is enormous. It can be calculated in tons of lateral thrust. During a climb, the risk multiplies. That is why the ritual is only performed during weather windows where the forecast guarantees winds below a critical threshold, often less than 30 kilometers per hour. In the cab, the operator always has a digital anemometer in view. It is his personal oracle. If the needle rises suddenly, the procedure is aborted immediately. The crane is lowered back onto the original mast and secured. But wind isn't just a hazard during the climb. It's the crane's constant condition. As it ascends, it's exposed to stronger and more turbulent currents. By design, the crane has a rotation freedom mode. When the wind exceeds the safe operating speed for lifting a load, the operator releases the turntable brake. The crane then stops fighting. It becomes a giant weather vane. The wind pushes it and it rotates freely, always orienting its slender boom to the airflow, minimizing the surface area of resistance and therefore the tipping forces. It's an act of engineering wisdom. Instead of resisting an indomitable force, intelligently yielding to it to survive. Operating in strong winds is an exercise in anticipation. Moving a 10-ton load in a crosswind is like handling a huge pendulum on an invisible swing. The operator must carry the load, anticipate its swing, and place it gently to counteract the wind's onslaught. Every day is a tacit duel with an invisible and tireless adversary. Vital ties. Anchoring the giant to the building's skeleton. The crane doesn't climb in absolute emptiness. As the building grows around it, it establishes a symbiotic relationship with it, a steel alliance crucial to its survival. This alliance is embodied in the tie-downs. Every 15 or 20 floors, specialized teams install high-strength steel braces as thick as a man's arm, connecting the crane's mast to the concrete cores or main columns of the skyscraper. These tie-downs are not simple clamps. They are structural elements calculated to transfer loads. Their function is threefold. First, they give the crane lateral stability. Without them, the mast, slender as a pencil, would behave like an incredibly tall cantilever beam, flexing dangerously in the wind. The tie-downs transform it into a continuous beam supported at multiple points, the building, drastically reducing its flex. Second, they relieve the load on the base. Part of the lateral forces are transmitted through the tie-downs to the building, which is designed to absorb them. Third, and most crucially, they make the crane and the building a single structural entity during construction. The building, though incomplete, gains rigidity by being attached to the crane tower, and the crane gains a safety net that anchors it to something more solid than its own shadow. Installing a tie-down is a precision job. An anchor plate is welded or bolted to the building's column. The tie-down is tensioned with hydraulic jacks to a specific load and then secured. It's another safety ritual, another knot in the rope that tethers the climber to the mountain. Without these ties, the dream of skyscrapers would vanish in an uncontrollable sway. The reverse problem. No crane is there to lower it. The paradox is reversed, but its logical bite is just as sharp. During construction, the crane climbed using the growing building as support and a guide. But now the building is complete. It's a sealed structure, with its elevator core operational and its facades closed. There's no clearance around the mast to assemble the climbing frame and easily perform the reverse process. Moreover, the idea of down climbing as it was climbed has an inherent danger. As the crane gets lower, it would lose the ability to reach its own components to lower them to the ground. And of course, there's the inescapable fact. The tallest mobile land cranes on the planet have a maximum reach that pales in comparison to the 300, 400, or 800 meters of a modern skyscraper. Even if one could get close, it couldn't operate in the dense urban environment among other buildings. It seems like a dead end. The crane is trapped by its own success, a prisoner of the height it conquered. The solution, once again, will not come from an external force, but from an internal intelligence applied recursively. If the crane was the tool that built everything else, the only tool capable of dismantling the crane is another crane, but one that can be born, live, and die on the edge of the rooftop. The appearance of the phantom crane, the roof auxiliary. Thus enters a smaller but equally crucial character, the auxiliary crane, often called a dolly crane or dismantling crane. It is the phantom tool, the one that doesn't appear in the glorious construction photos, but without which the story would have no ending. This crane is radically different. It is lighter, more compact, and designed with the opposite philosophy, not for climbing, but to be completely disassembled into pieces small and light enough for the main crane to hoist them one by one to the roof. Imagine the process. The tower crane, in its final great task, becomes its own midwife. With its hook, it first raises the base of the auxiliary crane, then sections of its small mast, then its folding boom, its motors, its counterweights. Each trip of the hook carries a piece of its own executioner to the execution site. On the roof, a specialized team of erectors receives these pieces. They work in an open but exposed space, with the wind lashing mercilessly, assembling this new structure with the same precision with which the large crane was assembled months before. When the last piece is bolted on, the auxiliary crane stands, complete and operational, in a corner of the rooftop. It is an act of creation in the sky, but its purpose is purely destructive, or rather, deconstructive. It is the egg containing the cuckoo that will devour its parents. Then comes a symbolic moment of profound faith in engineering. The auxiliary crane, newly born and tested, takes control of the sky. Its first mission is not to lift luxury furniture, but to dismantle the entity that gave it life. The main crane, which has been the heartbeat of the project for years, must now remain still and allow the smaller one to remove its parts. It is an act of calculated and peaceful cannibalism. The workers change cabins. The main crane operator becomes a mere spectator or an assistant following instructions to the letter. The auxiliary crane operator, now in control, initiates the final choreography. Trust here is absolute. If the auxiliary crane fails, there is no plan B. There is no other crane in reserve. It is faith placed in the structural calculations, in the quality of the steel, in the expertise of the assembly. The great crane, motionless, awaits its fate, like a samurai offering his sword. The changing of the guard is silent, but within it lies all the tension of the dismantling, the final act, disappearing. Finally, the main crane is reduced to its most basic configuration on the rooftop, a small section of mast, the turntable, the cab, and the motor. The auxiliary crane, which has been instrumental in this reduction, performs its last service to its creator. It completely dismantles the main crane. The cab is detached. The last sections of mast are unbolted and lowered. Each piece is catalogued, sometimes packed, and prepared for the final descent. And then comes the most poetic and self-referential moment of the entire saga. The auxiliary crane must dismantle itself. It is the only tool left on the rooftop. There is no other crane to lower it. Therefore, it must perform an act of assisted mechanical suicide. The riggers, using the building's pulley system, the freight elevator, or simply hand-rigging and their own strength, begin to dismantle it. First, they remove its jib, then its counterweights, then they dismantle its mast. The now light and manageable pieces are loaded into the freight elevator or lowered down the facade using pulleys. The last piece to leave the rooftop is usually the base of the auxiliary crane itself. When the filming helicopter or drone flies over for the last time, the rooftop is spotless. Only the anchor marks remain, small patches of repaired concrete, and the supports for the rigging that once held the giant. The crane has vanished. There is no trace of the machine that dominated the skyline for years. It's as if it was never there, a ghost that after building its home fades into thin air. The price of heaven. Counting the cost of an ascent. All this precision choreography, from the first bolt in the base to the last screw lowered from the roof, comes at a price that justifies every euro. A high-capacity, high-reach tower crane is not a tool to be purchased lightly. The manufacturing cost of a new unit can range from 500,000 to over 1 million euros, depending on its reach and capacity. But that's just the beginning. Transporting it to the construction site in a fleet of specialized trucks adds tens of thousands. The initial installation, including the foundation, mobile crane assembly and testing, can consume another 150,000 euros or more. Then there's the daily operating cost. Renting a crane of this type for a landmark project can exceed 2,500 euros per day. Added to that is the operator's salary, one of the highest paid in construction, earning between 300 and 500 euros daily, and the salaries of the signalmen and support engineers. A single tower crane installation costs thousands of euros in specialized labor hours and partial work stoppage. The final dismantling, with the auxiliary crane and the required elite team, can have a budget similar to the initial installation. Why is it so expensive? Because the productivity it generates is astronomical. Without a tower crane, building a skyscraper would be like constructing a Gothic cathedral with wooden pulleys. Every beam, every concrete slab, every facade panel, every air conditioning unit would have to be hoisted by hand or with infinitely slower and more dangerous systems. A tower crane can install in a single day what other methods would take weeks to complete. It accelerates construction by a factor of 5 or 10. In a project worth several hundred million euros, where each day of delay costs tens of thousands in interest and fixed costs, the crane is not an expense. It is the smartest and most profitable investment in the entire project. It pays for itself tenfold by preventing delays. It is the indispensable lubricant for the engine of vertical construction, beyond steel, the legacy that shaped the modern skyline. The history of the tower crane is inextricably linked to the skyline of our cities. Every leap in the capabilities of these machines has been a license to dream bigger. In the 1930s, the first climbing cranes, still rudimentary, made the Empire State Building possible, demonstrating that humankind could build profitably and safely above 300 meters. In the 1970s, more robust and better controlled cranes faced the winds of the 100-story twin towers of the World Trade Center, anchoring themselves to steel cores that rose like swords. In the 1990s and 2000s, the evolution was exponential. Cranes with greater lifting capacities, more reliable hydraulic systems, and lighter, stronger materials ushered in the era of the super tall. The construction of the Burj Khalifa in Dubai was a ballet of several tower cranes taking turns and attaching themselves to a structure that tapered like a needle, reaching altitudes where the air is so thin that operators sometimes need supplemental oxygen. Every new height record, Taipei 101, the Shanghai Tower, Merdeka 118, has been, first and foremost, a record of logistics and crane courage. Without the parallel evolution of this machine, the most ambitious plans would have remained forever on paper. The tower crane is the enabler. It is the key that unlocked the door to heaven for modern architecture. In the end, everything returns to the starting point, the builder's paradox. The tower crane is the material, tangible, and elegantly mechanical answer to a philosophical, practical problem. It is the tool that contains within itself the solution to its own existential dilemma. It doesn't need a deus ex machina god to bring it down from the sky with a lightning bolt. It carries within its design the seed of its own creation and its own dissolution. It is a brilliant testament to human intelligence applied to overcoming physical limitations. It didn't fight gravity by denying it. It used it, balanced it, tamed it with counterweights and calculations. It didn't fight height by avoiding it. It scaled it, incorporating it into its own structure. And when it finished, it didn't leave a rusting steel corpse at the summit. It recycled itself, piece by piece, in a final act of economy and elegance. It is the epitome of sustainable engineering in its purest sense. A machine that rises from the earth, fulfills a titanic function, and then returns to the earth without a trace, ready to be reborn in another work, in another vertical dream. So the next time you see that slender steel profile silhouetted against the sky of a city under construction, you won't just see a machine. You will see the walking solution to an age-old paradox. You will see a steel climber that was born in the earth, that learned to scale its own shadow, that held architects' dreams hundreds of meters above the ground, and that, once its mission was accomplished, vanished without a trace, like a mechanical ghost. Its assembly is not a simple sequence of steps. It is an epic narrative of engineering, where the protagonist is, at once, the architect, the worker, and the masterpiece of his own fleeting existence.